Welcome to The Deep Dive, the place where we take massive stacks of sources and distill them into the knowledge you need right now. For the last couple of years, when anyone says AI, we all pretty much picture the same thing.
The big ones.
The big guns, exactly. GPT, Claude, Gemini, these massive monolithic brains that run in these giant cloud data centers. The large language models, or LLMs, they just dominate the entire conversation.
They really do.
But today, we're digging into a more fundamental question, one that really drives the next wave of hardware. Is bigger truly always better?
Especially when you factor in real-world constraints.
Right. Things like power consumption on a device, the actual cost to manufacture it, and, well, the big one. Personal privacy.
And that's the critical pivot point, and it's exactly what the sources you gathered are all zeroing in on. So our mission today is to, move past the hype of the LLM generalist and dive into a completely different architecture.
Yeah.
One that's smaller, way more efficient, and structurally superior for portable tech.
The Recursive Language Model, or RLM.
Exactly. We're going to unpack how these tiny titans are really providing the roadmap for the next wave of on-device AI, whether that's in your smart glasses or, running a tiny robot.
Okay, so before we get to the revolutionary part, let's just quickly define the status quo. What is it about the architecture of an LLM that makes it so big and so dominant?
Well, to set that baseline, an LLM is, at its core, a neural network. It's almost always based on what's called a transformer architecture.
Right.
Its goal is actually pretty simple. Just predict the next word or token in a sequence. But, and this is the key, it gets good at this by being trained on just staggering amounts of data.
We're talking about, the entire internet.
Pretty much petabytes of text, training data that reaches into the trillions of tokens. And that scale, well, it demands a model of corresponding size.
Right.
So you end up with models that have hundreds of millions or even trillions of parameters.
Okay, let's unpack that. The scale is just incredible. But when you build an intelligence that has to read the whole internet, what are the architectural trade-offs that come with that size?
The defining feature is really how they use all those billions of parameters. It's through something called self-attention layers, which force the model to look at the entire context all at once, in parallel.
So it treats language like one long, flat string of words?
Exactly. It's a flat, sequence-wise process.
Yeah.
And this flat processing is what makes them such amazing generalists. Their strengths are, undeniable.
Deep world knowledge, for one.
Deep world knowledge, incredible zero-shot performance, meaning they can do things they weren't even explicitly trained on. And they just excel at general tasks like summarization or content creation. Plus, we know they scale predictably.
The famous scaling laws.
The bigger you build them, the smarter they seem to get.
So the LLM is this brilliant, broad-minded generalist who's read every book in the library. But that kind of brilliance has to come with limitations, right? We know they have some pretty significant weaknesses.
Oh, they absolutely do.
Yeah.
Despite all that compute power, they are really prone to factual errors.
Hallucinate.
The infamous hallucinations, right? But maybe more critically for certain tasks, that flat, sequence-wise processing means they really struggle to enforce strict rules, strict syntactic or logical constraints.
What does that mean in practice?
Well, they get tripped up by complex nested logic. Things like balancing parentheses in a math problem or keeping track of all the nested clauses in, say, a legal document.
And then there's the big one, the physical trade-off.
Of course. The extreme demand for compute and memory, which basically chains them to the cloud.
Okay, here's where it gets really interesting, especially for anyone designing, the next smartwatch or AR glasses. We're moving from needing trillions of parameters in the cloud down to just a few million running on a tiny chip. How on earth does an RLM manage that kind of reduction?
It manages it by fundamentally changing how it sees language. It shifts from seeing a flat sequence to seeing a hierarchical tree. The core idea is recursion. An RLM is built to explicitly call itself, or, a single optimized function within itself, on smaller and smaller substructures of the input. It's designed to mirror the way formal languages actually work.
So it's not trying to solve the whole problem at once. It's breaking a complex sentence or a piece of code down into tiny, self-similar sub-problems.
Exactly right. Imagine an LLM is building a house where every single piece of wood is custom cut and unique. The RLM, on the other hand, is built around a single, highly optimized neural function. Let's just call it $5.
The ultimate reusable Lego block.
That's a perfect analogy. The architecture, which is often based on things like recursive neural networks, it's all about maximizing the reuse of that one small, powerful core function. It applies it over and over to build up the meaning of the whole structure.
And that reuse is the secret to its tiny size.
It is. Because you only have to train and store one optimal function. You can get this powerful structural understanding with just a few million parameters. You just don't need hundreds of billions of unique weights.
That makes so much sense from a hardware and cost perspective. But does that focus on structure mean you give up all that broad knowledge the LLM gets from reading everything? I mean, where do RLMs get their training data?
That is the central trade-off, and it's a really critical point for you to understand. RLMs absolutely sacrifice that general world knowledge. They are specialists.
Okay.
So their data needs are way lower, maybe a few megabytes or gigabytes, but that data has to be structured. They need things like parse trees or defined grammars, not just raw text from Wikipedia.
But that specialization is also their key strength.
It's the source of their primary strength, structural precision. Because they're built from the ground up to process hierarchy, they naturally guarantee the well-formedness of nested structures. They're just inherently robust against the kinds of errors that plague LLMs, like generating code with syntax errors.
Okay, so this brings up a huge question. What's the fundamental operational difference here, especially around memory? We've all heard this term quadratic memory blowup. What does that actually mean for a device?
It's the Achilles heel of the LLM architecture. With that flat, sequence-wise attention, the model has to track the relationship between every single token and every other token in the sequence.
All at once.
All at once. So if your sequence has a length of, say, n, the memory you need grows at n squared. It's quadratic.
Can you give us an analogy for that?
Sure. Imagine you're reading a 100-page book. An LLM, to understand the last sentence, has to keep the memory of every single word from the first 99 pages active in its short-term memory, all at the same time.
Wow.
So if you try to process a 200-page book, the memory cost doesn't just double, it quadruples. And that quadratic blowup is the physical bottleneck that makes it basically impossible for these big models to run efficiently on small, battery-powered hardware.
That's a perfect analogy. So how does the RLM get around that quadratic trap?
RLM processing is hierarchical. Instead of reading the whole book at once, it summarizes chapters. The recursion naturally pushes information up the tree. Complex meanings are built from simple combined sub-meanings.
So it's processing local information and then combining it.
Exactly. Rather than processing all global information at once, this completely avoids that devastating quadratic memory cost. It's just fundamentally more efficient for anything that has structure.
And there's a huge side benefit here for the people who actually have to build and debug these models. Interpretability.
100%. The RLM is way more interpretable, since each step in the recursion maps to a clear, traceable subtask like, say, analyzing a subject-verb pair or simplifying math operator. You can literally see the model's logic tree unfold.
You know why a guide to an answer.
You know exactly why. It's not some impenetrable, high-dimensional black box like an LLM often is.
So if I'm a developer, the choice is really dictated by the task. LLM for broad, creative stuff, RLM when you need structure and correctness.
Precisely. You need a chatbot to write a funny poem. Use an LLM. You need an algorithm to simplify a college-level math equation or generate bug-free, syntactically perfect code. You have to use an RLM.
All right, let's pivot to the practical side of this. The learner is all about applying this knowledge. So why are RLMs so critical for this, say, 2024 to 2029 wave of wearable tech? Why can't we just shrink a GPT model?
You just can't. If we connect this to the bigger picture, you can't just compress an architecture that was designed for massive parallelism and flat sequences and expect it to work. You can't overcome that core quadratic memory problem.
So the RLM is critical because its architecture is inherently built for constraints.
It is. I mean, think about the physical footprint. An LLM needs hundreds of megabytes, often gigabytes, just for the model weights. An RLM can fit its entire core into 1 to 10 megabytes.
That's astonishing.
It really is.
Yeah.
We're talking about fitting a functional brain into the same space as a single high-res photo. This means they're completely compatible with existing low-power microcontrollers, like the ARM Cortex-M chips that are already in your watch or your coffee maker.
And a 100-fold reduction in size has to translate directly into power savings, which is everything for a wearable.
It's the difference between your battery dying in an hour versus lasting all day. The core model is so tiny that each inference uses dramatically less energy. And the beauty of recursion is that the work is spread out over these short, sharp bursts.
So the device can sleep between steps.
It can. It finishes one recursive step, goes to sleep to save power, and then wakes up for the next one. You're not keeping this massive piece of silicon constantly active, which is what LLMs demand.
And that efficiency feeds directly into the user experience, right? Latency. We want instant answers.
Correct. The responses are faster, they feel more real-time. Because that compact core can start delivering partial incremental answers as it finishes subtasks, you, the user, perceive the device as thinking instantly. You're not waiting for a result from the cloud.
But maybe the most compelling advantage for consumers today, especially with health data, is the built-in privacy.
Absolutely. This is non-negotiable going forward. Since the model is small enough to run entirely locally, all your sensitive data, your voice commands, health metrics, location, it never leaves the device.
So it solves the biggest privacy problem with cloud AI.
It completely eliminates the need to stream your sensitive data to some server halfway across the world.
That focus on privacy and using cheaper, existing chips must be a massive win for manufacturers. What are the advantages for them on cost and scalability?
The cost effectiveness is huge. A lower bill of materials, because you don't need high-end memory or cooling, but the real scalability win is the modularity of the architecture.
Right.
A manufacturer could standardize on one lightweight recursive core and just reuse it across their whole product line, glasses, a watch, a robot, just by tweaking a few parameters or adding tiny task-specific modules.
And those modular upgrades must be a game changer compared to retraining a whole LLM.
Oh, it's night and day. It allows for agile maintenance. If a grammar rule for a new programming language needs an update, you just swap out that one RLM function. You avoid the monumental cost and time of retraining and redeploying a billion-parameter model.
And we're already seeing this in practice.
We are. The sources point to some great examples. Think of live language translation on smart earbuds. The RLM parses a phrase, then recursively refines the translation for nuance, all on the device.
Or a health coach on your watch.
Exactly. It runs a symptom check, then uses recursion to ask smart follow-up questions, keeping the memory load tiny while giving you immediate context-aware advice without sending your health data anywhere.
So it really sounds like we're heading for this clear split. The giant generalist LLM in the cloud for creative work, and the tiny specialist RLM on our devices for precise private tasks. But, we rarely just choose one or the other. Is there a hybrid solution?
Absolutely. And that's where the most fascinating research is happening right now, blending the LLM's vast knowledge with the RLM's precision.
Okay, so what does that look like?
Well, one key trend is called grammar-guided decoding. You use the big fluent LLM to predict the next token, but then you feed that prediction into a dedicated RLM-style parser that validates it.
So the RLM acts like a strict live editor.
It's a perfect description. The parser forces the LLM's output to follow a strict recursive grammar. You get the creative fluency, but with guaranteed correctness.
You probably sacrifice some speed, but it's worth it for high-stakes tasks.
Exactly. Like generating error-free SQL queries or code where a single missing parenthesis could crash everything.
What else are we seeing?
Another technique, more software-based, is recursive prompting. Here, you prompt an LLM to break a big task down into subtasks. You're basically faking recursion in software. And then you call the same model again on those smaller outputs.
That's fascinating. You're imposing a structural solution onto hardware that wasn't designed for it.
You are. And finally, on the hardware side, chip makers are exploring tree-structured transformers. These are new designs that restrict the self-attention mechanism with a hierarchical mask. It gives the model an internal sense of recursion while keeping the benefits of the transformer framework.
That was a tremendous deep dive into the architecture that's really going to power the next decade of devices. So, to recap the core idea, LLMs are the massive, power-hungry generalists trained on flat sequences.
Right, for broad fluency.
And RLMs are the small, precise, energy-sipping specialists that reuse a single function to process tree-like structures, guaranteeing correctness.
The essential takeaway here for you is that the future of on-device intelligence isn't just about shrinking huge models. It's about picking the right architectural tool for the right physical environment. And the RLM architecture just inherently fits the constraints of edge devices, power, memory, cost, and privacy.
A fantastic summary.
So let me leave you with this provocative vision for, say, 2026 to 2030. Think about a fully modular AI marketplace. If this core RLM intelligence becomes standardized, tiny, and reusable, developers could start offering ready-made RLM modules.
Like app plugins.
Just exactly. Specialized modules trained for deep medical diagnostics or niche legal research or complex financial modeling that you could just download and swap into any device you own. Well, the question is, what are the implications for innovation and accessibility when that kind of specialized AI is running locally, privately, and affordably on demand?
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. please feel free to click on the link in the description below to discover more podcasts.